Okay, so our next speaker is Alexander Scott from Oxford, who is talking about local and global structure in combinatorics.
Great, thank you very much. Just to check, am I visible and audible?
You're visible and we can see your slides. It's all fine.
Fantastic. Okay, so just to start off, let me say thank you very much for the invitation, both to the organizers and to the Chan Institute. It's great to be part of this amazing event. Okay, so I'm going to talk about local and global structure in combinatorics. I'm very much aware that we have quite a diverse audience who won't be particularly expert in sort of my part of mathematics. So I'm going to try to be very concrete, and I'm going to very much avoid notation, and I'm going to hide a lot of the technical stuff, at least as much as I can. So maybe as a kind of starting point, let me suggest something very general, that the relationship between local structure and global structure, whatever those mean, it's a sort of subtle and complicated one, comes up in lots of different fields, and it comes up all across mathematics and the sciences. But thinking particularly about graphs, it obviously comes up in combinatorics, also in statistical physics, where you look at the kind of interaction between local constraints and global structure. Certainly in complexity theory, algorithmic complexity. Geometric group theory, where you might look at the kind of local structure of a Cayley graph and relate that to the group and the global structure. Also in model theory, where you might look at infinite structures, possibly via first order properties or again through local things. Okay, so the sorts of question I'm going to be interested in are what are the large scale effects of local structure? So if you know something locally, what does that tell you about what happens globally? Or going the other way around, if you have global properties, how do those manifest locally? Now, again, this is a huge topic, so I'm going to focus in on something very specific. But actually, to start out, I want to talk about the following question. So can you have a combinatorial object with no structure? What does it mean to have no structure? Can you be totally disordered, totally random? Okay, so the structure of the talk is going to be, I'll talk about this. So I'll very briefly talk about integers and then move on to graphs, which are really what I'm talking about in this talk. And then I'm going to focus on the Erdős-Heinl conjecture, which is an important conjecture in the field. And talk about some recent joint work. So with three co-authors, Maria Janowski and Paul Seymour, who are both at Princeton, and Sophie Sperkel, who's at the University of Waterloo in Canada. Okay, so let's talk about the integers first, just very quickly. So let's think about integers, or positive integers if you prefer. And let's suppose we divide them into k sets, or color them with k colors. So just sort of randomly if you want, or maliciously if you prefer. So you can ask, must there be very regular, very sort of nice substructures in there? Okay, the answer is yes. So more than a century ago, Shor showed that if you take so whenever you color the integers with finitely many colors, one of the classes has a solution to x plus y equals z. Okay, so actually a lot more is known. There are much more general equations. I mentioned this particular result because this gives a very simple proof that the mod p analog of Fermat's last theorem is false over, well, for sufficiently large primes p. So it's a very direct proof of that. About a decade later, van der Waerden showed that in any division of the integers into k sets, one of the classes has to contain arbitrarily long arithmetic progressions. So if you phrase it in coloring terms, monochromatic arithmetic progressions. Okay, now that's the start of a huge long field. So there's this work of Rado, Semeradi, Green and Tao, many others. So it's a large area. But the point is that you can't have just a completely random division. So you have to have structure appearing in one of the pieces. Okay, that's integers. What about graphs? How disordered can a graph be? Again, how totally random can a graph look? Okay, so I think we need to have some notion of order and disorder, and you could have various notions of that. But here's a notion, kind of very simple notion of order: complete subgraphs and independent sets. So complete subgraph is just a collection of vertices in your graph, all of which are joined. And an independent set, same thing, collection of vertices, but now none of them are joined. Okay, so all the edges are there, none of the edges are there. So the two extremes for what you can have. So there's those. I want to think of those as sort of very homogeneous sets. Okay, so basic question: if you have a large graph, does it have to contain a large complete subgraph or a large independent set? So does it have to have a large homogeneous structure? Okay, and this was answered a long time ago. Frank Ramsey showed in 1930 that if you have an infinite graph, then you have an infinite complete subgraph or an infinite independent set. There's a finite version of the following theorem. By the way, if you get distracted in the talk, then prove, and you haven't seen Ramseys theorem before, then actually it's a nice exercise to try to prove. The difficulty is not so much proving the theorem; it's actually spotting that it's a nice theorem to prove. The original motivation, in fact, was came out of logic. So the original paper is called something like on a theorem in formal logic. And there's a finite version of the theorem, which is which follows from the infinite version by a simple compactness argument, or you can prove it directly. So for every integer k, every sufficiently large graph contains a complete subgraph or an independent set of size k. Okay, so R of k here is sometimes called the Ramsey number. Okay, so what this says is that if I have a large graph, it contains a large homogeneous structure, complete subgraph or an independent set. Okay, but how large is large? So quantitatively, what happens? Okay, well, if you follow through the actually pretty much any simple proof of Ramseys theorem, you come up with a logarithmic bound. So you get the result that every graph on n vertices contains a complete subgraph or an independent set of roughly logarithmic size. So size at least constant log n. Okay, so the first question, can you improve this? Could you get, can you ask for more? And the answer is no. And the answer is no by looking at random graphs. So if you look at a random graph, typically it won't have a complete subgraph or independent set on more than logarithmic size. Okay, now I'm not generally going to include much in the way of proofs, so I'll include sort of one long discussion of a proof towards the end. But let me just indicate very quickly that, and this is actually an easy thing to prove. Just consider a random graph. So just for n vertices, and then for each pair of vertices, toss a coin, probability half, you put an edge, probability half, you put a non-edge, do that independently for each pair. And just count the expected number of independent sets or complete subgraphs of size k. So it's easy to check that, well, there's n choose k choices of vertices. If you want them to all have edges, well, there's what's 1/2 to the power k choose 2 probability that every pair is joined. And if you want to have no edges, that's the same probability, so that's that factor 2 in the front. So this is the expected number of complete subgraphs or stable sets, so independent sets on k vertices, and a quick calculation shows that that tends to 0 if k is a sufficiently large multiple of log n. Okay, and if the expected number tends to 0, then again it's easy to see that probability that you have any at all also has to tend to 0, just Markov's inequality. Okay, so what does this tell us? It tells us that the best you can do, I mean, it gives you in some sense a limit to how disordered you can be. So it says that down to logarithmic scale, all sorts of things can happen, but at logarithmic scale, you must have these very regular structures emerging, these complete subgraphs or independent sets. So that kind of limits how random can be. Okay, so that's sort of complete disorder in some sense. That's sort of the maximal randomness you can have. But how does the picture change if we're not quite completely random? So if we know a little bit about the local structure. Okay, now there are various notions of local structure we could have, and the simplest is subgraphs. So let's talk about subgraphs, and I need to be clear about what I mean by a subgraph. So there's two natural ways you can talk about subgraphs. So straightforward subgraph is just, okay, start with your graph, throw away some vertices, throw away some edges, and there you have a subgraph. Okay, so for instance, if you start with a complete graph, you can get anything as a subgraph. Complete graph, just choose how many vertices you need, and then choose whichever edges you need among those vertices. Okay, and you can get everything. So for example, a stable set, so an independent set. I keep saying stable because they're often called stable sets as well. An independent set you get by choosing some vertices, throwing away the others, and then throwing away all the edges between the vertices. Okay, so that's sort of a very natural notion of subgraph. There's an equally natural notion of induced subgraph. Here, you delete vertices, but you don't delete edges between the vertices. So if I delete a vertex, then, so let me be more precise, if I delete a vertex, then I have to lose all the edges instant with that vertex. But if I keep two vertices, then if they're joined before, they remain joined after. And if they're not joined, they remain not joined. So it's the subgraph induced by a set of vertices. So in particular, if I start with a complete graph, then all the induced subgraphs have to be complete because I pick any set of vertices, all the edges are there, and I'm not allowed to get rid of them. Okay, so in this talk, I'm only going to be talking about induced subgraphs. So from here on in, everything is an induced subgraph. So you pick your vertices and they tell you what edges you have. Okay. And we're going to be particularly interested in when there's some subgraph that doesn't occur as an induced subgraph. So if I have some H that I'm thinking of, we'll say that a graph is H-free if it doesn't contain an induced copy of H. In other words, there's no set of vertices so that if I look at the edges between them, I get something isomorphic to H. Okay, right. So what we know so far, so from Ramsey, is that most graphs have complete subgraphs, independent sets of no more than logarithmic size. Okay. Now there's a beautiful conjecture of Erdős and Heinel from the 1980s that if you have some local information, so if you know that you're H-free, then something very different happens. So they made the following conjecture. They conjectured essentially that if you're H-free, then the size of the largest independent set or complete subgraph that you can guarantee jumps from logarithmic to polynomial, by which I mean some n to the c, so fractional polynomial here. So say more precisely, for every graph H, there's some constant c that depends on H, so that whenever you have an H-free graph on n vertices, it has a complete subgraph or independent set with at least n to the c vertices. Okay, so it's a sort of huge change from logarithmic to polynomial size. Okay. Now, Erdős and Heinel did prove a partial result. They proved an e to the c root log n bound instead of n to the c. And actually, for graphs in general, that's the best known. That's still the best known bound, e to the c root log n. Actually, e to the c root log n is a curious sort of function. If you iterate it, then sort of a bounded number of times, then it's still subpolynomial. So it kind of takes little thinking to get an intuition for exactly how the scale works, but it's sort of bigger than polynomial, but sorry, smaller than polynomial, but bigger than polylogarithmic. Okay, so it's a gorgeous conjecture and a very frustrating conjecture, and it's one of the central conjectures in graph theory. Okay, so let me tell you what it's been proved for. So what graphs is the Erdős-Heinel conjecture known for? And the answer is actually embarrassingly few. So there's a few special ones. So it's true for complete graphs. That's actually easy from the off-diagonal version of Ramseys theorem. It's true for actually for two-edge graphs, but that'll follow from other things. For the three-edge path, so there's a structural characterization of graphs without a three-edge path. And there's a special graph called the bull, which is a triangle with two edges coming out of it, like little horns. That's proved by Janowski and Safra, again using purely structural techniques. Okay, so there's a few basic graphs. There's the easy observation that if it's true for a graph H, then it's true for the complement of H. If we go back to the statement of the conjecture is actually invariant under complementing H, because a complete subgraph in a graph G is the same as an independent set in the complement of G. So the complement is you just switch edges and non-edges. So if G is H-free, then the complement of G is doesn't contain an induced subgraph isomorphic to the complement of H. And so, and complete subgraphs and independent sets switch. So, so H and H bar are just equivalent as far as Erdős and Heinel are concerned. Okay, so if it's true for H, then it's true for the complement of H. And the third general statement, so there's a very nice result of Allenpak and Solomoschi, which is essentially a very clever counting argument. They showed that the class of graphs H for which Erdős Heinel holds is closed under substitution. So substitution, so substituting a graph J into a graph H, what you do is you take your graph H, take one vertex of H, blow it up, and you stick in a copy of J. Okay, so for example, if you take an edge and substitute an independent set into one end and the other end, you end up with a complete bipartite graph. So a set of vertices on the left, a set of vertices on the right, all the edges between them. All those edges correspond to the original edge in the single edge that you started with. Okay, so so it's known for, so we have those three, so the basic, the few basic graphs, complementation and substitution. And of course, all the graphs that you can get by combining these, the Erdős Heinel conjecture holds for those as well. So for example, complete bipartite graphs follow from combining the edge with substitution. Okay, there's one recent result I'd like to mention. So this is joint with Maria, Paul, and Sophie, which is that the Erdős Heinel conjecture holds when H is a cycle of length 5. So this was a special case that's been thought about by lots of people. It's been sort of it's been attention for a long time, and we finally, so building on some work of János Pák and István Tomon, we managed to show it for C5. This was featured in a recent article in Quanta magazine. So it's, even though it's only one graph, it is a significant step forward. Just to indicate the difficulty, we can't prove it for the 5 vertex path still. So that's the sort of the last interesting case on 5 vertices. So it's a very resistant conjecture. Okay, so is there a good strategy to attack the Erdős Heinel conjecture? So actually what I'm going to do is suggest a strategy and then show that it doesn't work, and then show that actually, well, it does at least give something interesting that's a little different. Okay, so here's a let's start actually by framing it slightly more generally. So so rather than just talking about H-free graphs, which is a very nice graphs, very nice class of graphs, let's frame it slightly more generally. So a hereditary class of graphs, that's just a class of graphs that's closed under taking induced subgraphs. So you can also say it express it by saying that if I have a graph in my class and I delete a vertex, I'm still inside the class. Okay, so it's sort of a natural class of graphs. And a class of graphs has the Erdős Heinel property if it satisfies if every graph in it, so if there's some constant C, so that every graph in it has the conclusion of the Erdős Heinel conjecture with that constant C. So in other words, every graph in the class, if it has n vertices and it contains a complete subgraph or an independent set with n vertices, with n to the C, sorry, vertices. Okay, so the Erdős Heinel conjecture says simply that the class of H-free graphs has the Erdős Heinel property. So there's some constant C, so that for every H-free graph, ... Okay, so so this is a class having the Erdős Heinel property. Okay, Now, there's a stronger conjecture, a stronger question, a property that we could ask for a class to have, called the strong Erdős-Heinel property. So roughly speaking, what this says is that if I have a graph, I could hope that there's two big subsets, two linear size subsets, and between them, either all the edges are present or none of the edges are present. So it's a bipartite version of this Erdős-Heinel property, but with the very strong property that both classes must have linear size. Okay, so more formally, a class has a strong Erdős-Heinel property if there's some delta, so that for every graph in the class, there are two sets of size at least delta n, where n is the number of vertices in the graph, so that those two sets, either they're complete, meaning all the edges are there between them, or they're anti-complete, meaning that none of the edges are there. Okay, so they're disjoint complete or anti-complete. Okay, and there's an easy lemma, just look at a little analysis that checks that the strong Erdős-Heinel property implies the Erdős-Heinel property. Roughly speaking, what you do is, given a big graph, you find two sets that are complete or anti-complete, and inside each of those, you recurse, you find two sets. Okay, so your first two sets have linear size, your second sets, so inside each side, you find a linear size pair, linear in the size of the set, that are complete or anti-complete, and you keep going. And that gives you a kind of nicely structured kind of hierarchy of subsets. You have to check how big they are, and you have to extract either a complete graph or an independent set from those, but it's not hard to do. Okay, so it's fairly routine to check that the strong Erdős-Heinel property implies the Erdős-Heinel property. Okay, so, okay, well, we might then hope to prove, rather than the Erdős-Heinel property, maybe we can prove the strong Erdős-Heinel property. Okay, so it's nice. Somehow working with bipartite properties is nice. Maybe we could use that to prove the Erdős-Heinel conjecture. Okay, so you sit down and ask, when does the strong Erdős-Heinel property hold for the class of H-free graphs? What could we conjecture? Okay, well, here's the first bit of bad news. H has to be a forest. And you can show that by just looking at sparse random graphs. And so if you just look at a sparse random graph with edge probability about log n over n, it's easy to show that you don't have many copies of H, so you can just delete any vertices that contain a copy of H, and what's left doesn't have either of the structures you're looking for. So it doesn't have H. If H is not a forest, it doesn't have H, and it doesn't have a large pair that's anti-complete. Okay, so that's a straightforward random graphs argument. Second piece of bad news is that the complement of H must be at the forest as well. So just take the same argument, apply it to a complement to a very dense random graph, or equivalent to a complement to a sparse random graph. Okay, so if you're going to get the strong Erdős-Heinel property, then H has to be the forest, H has to be the complement of the forest, and then just you count and you find that H has at most 4 vertices, and the conjecture is already known for all these cases. So it seems that the strategy doesn't give us anything at all. Okay, so insert sad face. It seems like, fail. But here's an interesting result. So, a result from just over 5 years ago by Nicolas Bousquet, Aurélie Legout, and Stéphane Thomasset. So they predict this very nice result that if we forbid 2 things, then we do get the strong Erdős-Heinel property. Okay, so they said if neither G nor its complement contains a path on T vertices as an induced subgraph, then you get the strong Erdős-Heinel property. So let me say that more succinctly. If we exclude both a path on T vertices and the complement of a path on T vertices, then you get the strong Erdős-Heinel property, and therefore also the Erdős-Heinel property. In other words, the Erdős-Heinel conjecture would say if I forbid one graph, I get this nice conclusion. So I get these large independent sets or complete subgraphs. And this says, well, look, let's forbid 2 graphs, one very sparse path and one very dense, the complement of the path. and then we get the conclusion. Okay, so this result was extended a couple of times, and then the following general conjecture was formulated. So let's take any tree T. So equivalently tree or forest, doesn't matter what you use, as every forest is an induced subgraph of a tree, a bigger tree. So let T be a tree, then if you look at the graphs so that neither the graph nor its complement contains an induced copy of T, then you have that class has the strong Erdős-Heinel property. Okay, and again with Maria, Paul, and Sophie, so we proved this. So let T be a tree, so if exactly conjecture, if you don't contain either, so that should be T or the complement of T, sorry, no, it should be G. It's neither G nor its complement contains the induced copy of T, then you get the strong Erdős-Heinel property. Okay, and immediate conclusion, it follows that if we forbid a tree in the complement of the tree, then the resulting class has the Erdős-Heinel property. Okay, so one graph, we don't know how to do it, but if you forbid two graphs, one very dense, one very sparse, then we can do it. You do get this sort of larger order. Okay, just as an aside, we have to exclude a tree and the complement of a tree. And since every hereditary class is characterized by the graphs that do not occur, so the minimal graphs that do not occur as an induced subgraph, this result actually characterizes hereditary classes with this strong Erdős-Heinel property. Okay. Here's another interesting result. So this is Marc Bonamy, and again, Nicolas Bousquet and Stéphane Thomaset. They showed a slightly different result. So now neither G nor its complement contains a long induced cycle. Okay, so a cycle is just you run around in a circle, so it's like a loop. So every vertex has two edges coming out of it. So if neither G nor its complement contains an induced cycle of length at least T, then you again get the strong Erdős-Heinel, the strong Erdős-Heinel property. Okay, by the way, it's a short and beautiful proof. So again, it can be generalized, and we should actually, if you forbid in both G and its complement an induced subdivision of any graph H, then you get the strong Erdős-Heinel property. So subdivision is just take your copy of, it's sometimes called a topological copy of H. You take your graph H and you're allowed to insert edges, you're allowed to insert vertices along the edges. So for each edge of H, you're allowed to replace it by a path of any length you like. So for example, a theta, so you could take any three paths where the beginning and end point are the same, and those are all subdivisions of, well, the multigraph where you have two vertices joined by three edges. Okay. Right, let's go back to the earlier theorem I mentioned. So if you forbid both the tree and its complement, then you get the strong Erdős-Heinel property. So I'd like to give you just a very quick hint of the proof. So I'm going to hide lots of detail here and just give a very quick bit of flavor. Okay, so one thing I wanted to actually was mention a very important tool that's used in all over graph theory called Semrada's regularity lemma. Informally, this says that you can take any graph and divide it up into pieces so that between the pieces, you get something that looks a bit like a random graph. Okay, so it's sort of an amazing result, a very surprising result. It says somehow every graph looks random. Okay, take any large graph, you can divide it up into a bounded number of pieces, and then look at what happens between all the pieces. It looks like you have a collection of random graphs. Now, I'm lying very slightly. I'm lying by epsilon, and I'm lying by epsilon in every possible way. So let me make it a little bit more precise and more truthful and completely truthful. But so I'll give you a very quick couple of definitions. So you don't need to take this away for the rest of the discussion, but I did want to mention the tool because I think it's a nice one. So first of all, what do we mean by looking random? So if I've got two sets of vertices, A and B, let's write DAB for the density of edges between them, so what proportion of possible edges to there. And we'll say that the pair is epsilon uniform if whenever we take a large subset of A and a large subset of B and look at the density between those subsets, it's close to the density between A and B. Okay, and large means at least epsilon proportion, and close means a difference at most epsilon. Okay, so statistically, large subsets are joined with roughly the number of edges you expect.
You have 5 minutes of regular time left.
Okay, thank you. And a partition is epsilon regular. So I'd like to say, if I've divided up so that every pair of sets in the partition is epsilon uniform, can't quite do that. So we have to throw away a small set of vertices to allow to throw away proportion epsilon of the graph. And then the rest of the partition, most of the pairs are epsilon uniform, but all but a small fraction. So at every stage of this, there's an epsilon approximation going on. So you throw away epsilon fraction of the graph, you're allowed to ignore epsilon fraction of the pairs, and epsilon uniformity of a pair means, well, if I take at least an epsilon fraction of each side, I'm within epsilon of the density I expect. And Semirady's regularity lemma basically says that every graph has an epsilon regular partition. So there's a typo here, but let's ignore that. It just says if I take enough pieces, then I can find. I mean, if I'm allowed to take enough pieces, then I can find an epsilon regular partition. Okay. By the way, that enough pieces that grows very, very quickly. Okay. Now, a useful application of the regularity lemma is the following nice result of Rödl from the 1980s. About H-free graphs. It says that if I take an H-free graph, then I have a big piece of the graph, linear sized piece of the graph, that's either very dense or very sparse. Okay, so H-freeness is sort of telling us that the graph is, in some sense, it's sort of not as random as it might be, because there are bits that are very dense, bits that are very sparse. Now, don't forget, we're looking for bits that are complete subgraphs or independent sets. So very dense or very sparse isn't enough, but it's helpful. So every H-free graph has a linear size set, and again, linear hides a constant, with density at least 1 minus epsilon or at most epsilon. Okay, so in our application, when we're looking at H-free graphs, we can assume that our graph is either very sparse or very dense. And since the theorem is invariant under taking graph complements, we can just assume the graph is very sparse. Okay, so actually what we end up doing is proving a one-sided version of the result. It says if you have a sparse graph, so small maximum degree, and you don't have an anti-complete pair, so two linear size sets with no edges between them, then you have an induced copy of the tree. Okay, so with one eye on the clock, I'm going to now hint at how the proof goes, but just very, very quickly. So roughly speaking, so you fix a tree T, choose ridiculously small constants, and divide your graph up into linear-sized blocks, very small linear-sized blocks. And we're going to look for a rainbow copy of T. In other words, we'll look for an induced copy of T with each vertex in a different block. And the basic strategy of the proof is so you start with this great big collection of blocks, and we're going to refine the collection to get more and more niceness in the structure. So we're going to get rid of complexity wherever we can and move towards a simpler and simpler structure. Okay, so there's various sorts of structures we can get rid of. So for instance, if we have a matching, so that's just, here we have some blocks. So the rectangles are blocks. The circles are subsets of blocks. And if we have, each block is covered, meaning everything in this first circle, everything in this first rectangle is adjacent to something in the first circle, but nothing in the other circles. And similarly in the second rectangle and third rectangle and so on, then there's some hope for working by induction, because if we take our tree T, delete a leaf from the tree, an end vertex of the tree, if we can find a rainbow copy of that smaller tree, then we can use one of these circles to add on the leaf. Okay, so there's sort of induction on the size of the tree. So we can assume we don't have a matching. And then I will just go quickly past these. I'll just say, we look for how subsets of blocks can see other blocks. So do they see everything in the block? Do they see just some things in the block? And we look to refine that and make that more and more regular. And I think maybe I'll skip this. I'll just say that we work so that if there's a particular pattern that you're looking for, either it occurs absolutely everywhere in every possible way, or it doesn't occur anywhere. So repeatedly, we shrink the blocks to get rid of patterns if we can. We're using Ramseys theoretic arguments a lot. And ultimately, we end up with these large collections of trees. So we end up with, we order the blocks, we have trees that grow from the left, trees that grow from the right, and we try to extend to get larger trees. Okay, I will actually skip all the details. Roughly the pattern is that we're going to use the n blocks, and we'll either extend the right growing trees or the right rooted trees or the left rooted trees to form bigger trees. And if we extend with the vertex in the right n block, hopefully we get a bigger right rooted tree. In the left block, a bigger left rooted tree. So here we are. I've taken some right rooted trees, I've joined them together in an n block, and that gives us a bigger right rooted tree. Okay, now there's a lot of detail that I'm skipping, and sometimes it works, sometimes it doesn't. In the cases it doesn't work, you have to do something a little bit different. But that's sort of roughly what we're doing. So there's lots of cleaning up the structure, cleaning up the structure, cleaning up the structure iteratively, until you get something ultimately you can handle. Okay, so I'm running out of time, so let me just finish with a few points. So the Erdos-Heinel conjecture, so I've focused on this one problem very much for this talk, but it's a central problem in combinatorics. And after 30 years, it's still frustratingly only known for a small family of graphs. So we were very happy that we proved it for C5. We wanted to do that for a long time, but I have, and the rest of the group as well. But still, there's infinitely many things we can't yet do. It's not even entirely clear whether the conjecture is true or not, and it would be very interesting either way. Okay, a kind of general point that the relationship between local and global graph structure is a subtle one. It's what arises in many fields and presents important mathematical challenges. So all the fields I mentioned earlier, and certainly statistical physics is a good example. Machine learning actually is another good example where you have local information, but you're looking at something more global and want to infer something about the global structure or predict. Okay, an effective approach. So one thing I've been trying to hint at in the talk is that it seems to be very effective to combine structural extremal understanding with random or pseudo-random techniques. So this combination of structural and random, it seems to be very effective, but certainly in combinatorics it's proved tremendously effective in the last 30 years. And finally, I want to say thank you. It's been great fun giving the talk.
Okay, well, thanks very much. Are there any questions?
Yang.
Yang, you have a question?
Thanks, Alex, for that lovely talk, and thanks for actually putting into context the quantum magazine that I read. Now gives me a mathematical context over that. So that is really, really exciting stuff. So I think we may have discussed it. Earlier this year, I was playing with graph properties. This was you mentioned machine learning, so it's perfect. So I was working with Yao on something that smells similar. So we were looking, among other things, for Ricci flat graphs, finite graphs, which are up to some definition. So an experiment that we did was to just throw in a binary classifier of graphs that have this property or not have this property, and you could imagine some generic machine learning algorithm could actually distinguish them to some degree. So I wonder whether you just throw in a couple of million finite graphs with strong Erdos-Heinel or Heinel property, and I wonder whether I can imagine a classifier would be able to do it, and I wonder whether this would give any insights toward to actually help improving this conjecture?
Okay, thank you. That's a great question. So I think two things to say about that. So one is there's sort of a subtle question about what your sample space looks like. So so when you throw in a kind of population of graphs, the way you generate those graphs or find those graphs is very important. And if you're kind of inserting, if in the way that you generate them, you're kind of creating certain properties or making certain properties likely, then those are the things that might get picked up by your classifier. So for example, if you look at a typical triangle-free graph, so if you just take the space of all graphs and take a random triangle-free graph, most of them are actually bipartite. So if you're just sampling typical triangle-free graphs, and most of them are bipartite because if you take a complete bipartite graphs can be very, very dense. Whereas as soon as you have something sort of slightly more spread out, then the density drops a lot. And the density means that sort of high entropy, there's lots of things, lots of graphs you can get. So in some sense, by generating them at random, just uniformly, you embed the property of being bipartite. And so that's sort of the thing that you pick up. So there's an interesting question there as to, when you're looking at particular spaces, what are they actually reflecting? Are they reflecting the question, or is there something structural in them as well? Which is also very interesting. But yes, absolutely, if you can get a classifier that does reasonably reliably recognize instances that have some particular property, then it's very interesting to try to reverse engineer that a bit and sort of figure out, is there something they're picking up that we can actually understand? So I mean, it's interesting problem even just to classify, but then actually maybe to figure out what's going on. So I think that would be absolutely fascinating.
Are there any available databases that does this? I mean, that has these properties that you mentioned today encoded?
I mean, the trouble is that the number of graphs grows so quickly. So if you want to look at all graphs, for example, then they're growing like, on n vertices. It's not just exponential, because there's n vertices where n choose 2 possible edges, so that the number of possible graphs is growing like 2 to the n squared. So there are databases of kind of various small instances. I mean, the other issue would be that if you're talking about some small polynomial growth, then probably you need quite large graphs to start extracting. The difference between logarithmic and polynomial, once you throw constants in the front, you're going to need to look at really large examples to start to pick things up.
Thank you.
Any more questions?
Hi, can I ask 2 questions? The first one is there any easy intuition for why the conjecture was made in the first place? And the second one is, can you use the regularity theorem to generate random numbers? Would that make for a good random data generation algorithm? Or is this too much of an overkill?
Okay, so for the first question, yeah, so it's a very natural question to ask, what if I forbid some local structure, what does that tell me about the graph as a whole? Does the behavior change? And if you forbid a triangle or a small complete subgraph, then it follows immediately from Ramseys' theorem. So there's a natural context there. And Erdős and Heinel did prove that you get some growth. So they have this e to the root log n behavior. So that's already a bit of an expansion. So it's much bigger than any polylog function, but sub-polynomial. So it's sort of natural in that sense. And they had it for a few other small graphs as well. So they conjectured before the substitution property came along. So it is a reasonably natural, very bold, but reasonably natural conjecture. And so far, I think this sort of medium scale structure is very hard to generate at random, very hard to kind of create examples. So there's it's sort of why it's so much of a gray area. So it's a similar phenomenon with graph coloring, by the way. As far as random numbers go, so well, if you try to do anything with some radius regularity lemma that's algorithmic, you run into the problem that the constants are so large. So so implicitly, I didn't highlight it, but you have an epsilon, and then you have, if I have enough pieces, if I'm allowed to have enough pieces in my partition, and enough pieces is actually a tower function. So 2 to the 2 to the 2 to the 2. Tower of height 1 over epsilon to some power. So
Okay.
So it's absolutely hopeless for anything algorithmic.
Okay. Okay. Thank you.
Okay, well, thanks very much again.